Tradeoffs, Part 2, Braking and Redundancy. Welcome back to The Explainer. Today we are wrapping up our deep dive into drilling rig electrical drive topologies. So in Part 1, we built a really massive case for one specific layout, but, in rig design, there's absolutely always a catch. So let's jump right back into this and finish the puzzle.
Let's just do a super quick recap. You'll probably remember that multi-drive systems had an absolute winning streak when it came to physical footprint and power quality. Because they share a common rectifier and a DC bus, a multi-drive setup cuts down on heavy switchgear, it saves a massive amount of space and weight, and it totally eliminates the need for individual harmonic filters on every single unit. So honestly, it sounds like an engineering slam dunk, right?
But that brings us to a really glaring question. If multi-drive wins on space, weight, and cost so effortlessly, well, why isn't it just the universal standard used for absolutely everything offshore? Like, what exactly is the catch that keeps engineers from just picking it automatically every single time?
Well, the answer really comes down to how these two distinct architectures handle two vital things: braking and redundancy. So let's tackle braking first. When a heavy drilling motor brakes, say, when the drawworks is lowering a massive load of drill pipe, it essentially acts like a generator. It creates a ton of energy that has to go somewhere, safely. And this leads to two completely different ways of managing that massive influx of power. You can either dump it into individual resistors, or you can pool it into one combined braking resource.
Picture a single drive system. In this setup, every path is completely isolated. Because each single drive unit is fully independent, it's basically forced to isolate that braking energy. That means every single joule of regenerated power from a braking motor is pushed straight into dedicated individual braking resistors that are bolted directly to that specific unit. And all that energy, it's entirely dissipated as wasted heat.
Now contrast that with a multi-drive setup. Instead of having a bunch of isolated, independent resistors scattered all over the place, multi-drive utilizes that shared DC bus. Because every motor's braking energy lands on that exact same bus, the system can actually use one combined braking resource that's sized for the whole group. You don't have to outfit every single drive with its own maximum capacity heatsink.
And honestly, this illustrates one of the most elegant engineering efficiencies you'll ever see in rig design. It's called motor-to-motor braking. Because these inverter units share a DC bus, the braking energy from one motor, like, say, a motor that's lowering a heavy load, can flow directly across the bus to feed a second motor that happens to be accelerating or hoisting at that exact same moment. The accelerating motor directly absorbs the braking energy. There are literally no resistors involved at all for that transfer. It means way less wasted energy, and it allows for significantly smaller, lighter resistor banks overall. Single-drive units simply cannot do this.
Okay, but here is the dramatic reversal. Sharing a bus means you are sharing risk. One rectifier fault equals all motors down. This is the massive redundancy cost of a multi-drive system. If you lose that single, common supply unit, the common rectifier feeding the bus, it instantly blacks out every single inverter and motor connected to it, all at the exact same time.
When you compare them directly, the contrast is super stark. With the single drive, fault isolation is just built right into the architecture. If one unit fails, you only lose that one specific motor. All the others keep running completely independently. But with multi-drive, that common bus risk is obvious. A single point of failure at the rectifier takes down the entire group. And for critical, redundant applications on a rig, that is a real, high-stakes design consideration, not just some minor footnote.
So the absolutely crucial point here is balancing that electrical risk against physical reality. Let's pivot just briefly back to Fprit and cabling. Single-drive layouts demand these really dense, individual, full-rated feeder cables running all the way from the switchboard to every single unit. Multi-drive, on the other hand, gives you a compact shared bus bar with much lighter branch cables, because the inverter is just clustered directly around that shared bus.
And when we look at the real-world yard benefits, multi-drive offers a massive advantage during rig construction. You have fewer cable pulls, and the ones you do have are much shorter. This directly shifts incredibly expensive, schedule-critical wiring labor off the shipyard floor and straight into the vendor's controlled factory environment, where all those internal cabinet connections are already pre-wired and pre-tested. That is a real game-changer that can legitimately shorten a rig's entire construction schedule.
But you really have to look past first oil here. Over-engineered single-drive layouts pack your cable trays incredibly densely. And it's not just a headache during installation. Congested trays mean severe physical maintenance difficulties for years to come. I mean, think about it. When a maintenance tech needs to trace a fault or add a cable 5 years down the line, an overpacked tray makes their job exponentially harder.
Okay, let's step into the role of the lead engineer for a second. Imagine you are designing redundant drawworks drives for a rig. Now, in this specific application, losing all your hoisting motors simultaneously is absolutely unacceptable. It's a massive safety and operational hazard. So what do you choose, single drive or multi-drive?
Well, if you said single drive, you made the right call. For critical redundancy, single drive wins every single time. That inherent electrical isolation completely prevents a single failure from cascading into the other units. Yes, you sacrifice space and cabling convenience, but you do it to ensure that if one drive trips, you still have the power you need to safely control the well load.
So let's pull everything from this two-part explainer together into a definitive decision matrix. Picking a topology really isn't a guess anymore. Multi-drive is the undeniable winner when it comes to space, weight, cost, centralized harmonic filtering, and that awesome motor-to-motor braking efficiency. It saves you steel, copper, and precious shipyard time. But consider that final variable. When absolute fault isolation and redundancy are non-negotiable, single drive stands alone as the clear winner.
So we want to leave you with this final provocative thought. The right engineering call entirely depends on which failure mode your rig design can least afford. Do you prioritize maximum space efficiency and lower upfront cost, or do you prioritize absolute isolation against a catastrophic simultaneous failure? Basically, which risk are you actually willing to accept? Keep this framework handy the next time you're reviewing a single-line diagram. Thanks so much for joining us for this explainer, and as always, keep learning.